person will make a report on a subject close to this, close to what we discuss. But while you are preparing for a talk, we shall have some other grown-up participant of the seminar talking about another subject close to the deformation quantization. I think it will be either все прекрасно. Okay. So next time there will be either a talk by Pavel about quantum groups. Oh, sorry, something is wrong with this. What's it? Yeah. Sorry, too many wires. I'm trying to disentangle it, and that's not happening. Okay. I'm going to do it like this. Just use it. Okay. So next time there will be either talk by Pavel Saponov about quantum groups and other algebraic constructions which lie behind the quantization theory. Or there will be talk by Alexander Zhuglov about quantum integrable systems, commuting differential operators and their classification and so on. So one of these subjects will be treated, and I hope, but the problem is that we need to make it so as to make the whole story coherent, so that you see that these three subjects are actually close together. So I cannot yet tell which strategy we shall choose, but whatever strategy will be, you'll have it another talk. Okay, and now my purpose for today is to conclude the construction of Fedosov's quantization, and let me recall the basic ideas of this construction. So suppose we have a symplectic manifold M, and omega is the symplectic form. So omega is a differential 2 form on M, which is non-degenerate. And closed. It can be actually exact, it doesn't matter. Then we can introduce the Poisson bracket on functions, smooth functions of this manifold, which verifies all the standard properties which should hold for Poisson bracket. And one can ask if there exists an associative product, star product, on functions, well, or rather on formal power series with coefficients and functions in the form of variable h bar, which is h bar linear, and also verifies one important condition, that up to the second degree in h bar, the star product of f and g is given by the following two terms. It is the standard product of f and g, and also the second term is h bar times the Poisson bracket of f and g. And all the rest are terms with h bar to the second power and higher. There were also two technical conditions, and also one can ask how many different star products there exist. So this second question which is also very important. I'll put it here. So the second question is also very important. It's classify all different star products. Just to say how many different star products they exist, but the problem is to describe the equivalence relation up to which we shall distinguish the star products. So I'll discuss this equivalence relation a bit later when we come to this problem. So now I'm just going to describe philosophers' ideas and give some hints as to how these ideas are actually achieved in order to construct the star product. So the first idea, which I actually explained last time, was to embed linearly the space of all functions, or rather function-valued formal power series, into certain associative algebra denoted by W hat, so that the image of this embedding of this, well, philosophy denotes this map by Q, so it's that the image of Q of C infinity H bar is certain subalgebra then the star product can be written as simple as in a very simple way as just a composition of the inverse map Q minus first applied to the product of the images of F and G. As you see, since the image is a subalgebra, the product of two elements is again an element in the image. So when we just take the inverse, we obtain something in the original space. The associativity condition is evident from the associativity of the product in W hat. And I think last time I even described the main idea of how this W should be constructed and how this algebra will be constructed. So let me now give the details which I missed last time. Okay. So first of all, the construction of the algebra W hat. So there are different ways to construct this algebra. All these constructions lead to the same object, definitely. But and I roughly sketched this construction last time, but now it is time to fill in the details, so I pretend I have never spoken about this and just start from the scratch. Okay, so suppose I have a coordinate sheet in coordinate map in the manifold M. That is to say, have local coordinates x1, x2n, and to these coordinates you can associate a standard basis in the cotangent space. So the basis in cotangent space is given by dx1, dxn, right? Okay. So what you do now, you actually consider the functions, the coordinate functions associated with this basis. So these coordinate functions okay, of course we need to fix the point in the base to describe this basis. So of course this basis is actually a field of basis. There is a basis in every point, but we'll fix the point once for a while. And then we have coordinate functions y1, sorry, y2n on t upper star x dot m. Roughly speaking, yi applied to how do you call this, to the vector, to the covector xi of the sum, okay, xi j dxj will be equal to just delta, I think it's psi j delta I j, something like this. Yeah? So these functions, these linear functions, they are elements actually elements in it's important to keep the trace of upper and lower coordinates or indices, so I'm trying to do this. They have elements in the tangent space. I hope I was right to do this, right? So if you take a vector and apply it to a covector, so you obtain an element, right? Okay. So you have this local set of elements. You can regard y1, actually y2n, as a local basis again in tm, again associated with the same coordinate system. Okay, so what we do, we construct the Weil algebra. We take the complex valued polynomials, non-commutative polynomials in y1 to y2n, right? I just hope that I'm not mistaken the indices. It should be a disaster if I make this mistake and take upper indices instead of lower indices. Oh yeah, dx2n. Yeah, 2n, because I took symplectic manifold, and symplectic manifold is always, the dimension is always even. No, I believe I have correctly written down the indices upper and lower. Okay. So what we do next, we quotient out these non-commutative polynomials by the relation that the commutator of yi and yj is equal to h bar divided by square root of -1 pi ij, where pi ij is just the coefficients of the inverse of the symplectic form. Of course, this formula works for just one point, or at most locally, when we have this coordinate system associated with this local coordinates. Then we have this algebra. Actually, everything depends on the point in the base. So you have a kind of local family of algebras, associative algebras. Over the coordinate chart parameterized by the points on the chart. Yeah? So for every point x dot x0 in this chart, you have this algebra. Now what happens if you change the coordinates? Let us check it. So now we shall see the power of upper and lower indices. So we know that pi ij is the covariant tensor of degree 2. So pi I prime j prime is equal to dx I prime dx I dx j prime dx j pi ij. The summation of all repeating indices is assumed. And similarly, y I prime is equal to d x I prime d x I y I. So what happens if we substitute these relations into these formulas into this relation? Well, it is easy to compute, because y I prime and y j prime now shall be replaced with these formulas. So we get dx I prime dx I dx j prime dx j, commutator of y I with y j. And now according to the relation, it should be equal to h bar divided by square root of minus 1 times pi ij. But now according to this formula, this is precisely, this combination is precisely pi I prime j prime. So as you see, the change of coordinates preserves the relation, and in this way we see that these families of algebras, associative algebras, globalize to a family of associative algebras parameterized by points of the whole manifold M. So we see, we shall denote this family by W C. Well, this C is necessary to distinguish the complex valued while algebra with real valued while algebra. We could have avoided the complex coefficients, but Fedosov actually preserves them because for some physical reasons. In physics, it's important to know that the commutator of momenta and coordinates are imaginary values.
The reason is very simple, because physics are interested in Hermitian representation.
Yeah. Yeah. Well, from pure mathematical point of view, there is no such need, but we shall preserve.
If you study.
Yeah. So by the way, it means By the way, this means that since we have introduced the square root of -1, you should had to introduce the square root of -1 into the formula for the star product. I forgot to do this, but actually it should now look like this: fg plus h bar divided by twice square root of -1 f comma g plus small of h bar. So anyway, we obtained this family of Weil algebras over M associated with the symplectic structure omega, and I should denote it like this. There are few different ways to look at the same construction. In my opinion, the most geometric one is to consider the symplectic frame bundle. So if you know what are frame bundles associated with vector bundles, then you can follow me. If you don't know, it is worth taking a look in the literature. But anyway, so if you have a manifold M endowed with symplectic structure, then you can construct the frame bundle of symplectic frames over M. This is the frame bundle which verify the symplectic property. I mean, they are canonically symplectic. The symplectic form in these frames should look in a canonical way. That's how you define a symplectic frame. Then a symplectic group acts on this frame bundle from the right. Actually, it's a principal bundle with a symplectic structure group. And we use this symplectic group action. And actually, if we take the symplectic group action on R to N, and what we obtain will be just the tangent bundle of M. Right? But actually, we can associate with any R to M the Weil algebra with respect to the canonical symplectic form. Oh, I forgot to say that you have to introduce H here, so probably it is worth to have H marked separately here. Okay, so you can take the canonical symplectic form on R to N and construct the Weil algebra. And symplectic group acts on Weil algebra. Since it acts on R to N, preserves the symplectic form. So now you can take the associated vector bundle like this. And moreover, since this vector, since the action of symplectic group preserves the product, this is again a bundle of associative algebras, associative algebra bundle. Then what we have just constructed is precisely this bundle. Now we can construct.
I'm sorry.
Yeah.
Could you say what is the fiber?
The fiber of what?
Point of this bundle.
Here, just symplectic group.
Yes.
SP to N. The symplectic group is the bundle, is the fiber.
Okay.
Yeah. The fiber is collection of all symplectic, canonical symplectic bases in R to N. So it can be identified with the symplectic group itself. Since symplectomorphism seems actually are just the maps which send one symplectic basis to another symplectic basis. So we can identify the group with the fiber. Okay, so this is a fiber bundle, and then we can define the algebra itself. Now the algebra, in terms of the algebra, in terms of this fiber bundle, the algebra we need, I denoted by W sub H of M, is just the algebra of sections, of smooth sections of this fiber bundle. So what is a section of a fiber bundle, a vector bundle? Section is a map from the base to the fiber bundle itself, to the total space, which goes to identity if you compose it with a projection. So P is projection from the fiber bundle to the base. So this should be identity. In other words, it is just a map which sends every point in the base to the fiber which lies above this point. If you are not familiar with this kind of constructions, or if you find them too abstract, you can look at this in local coordinates. And then every section, every element, let's call it alpha. Alpha in, okay, A, way better to say A. Here, element A here in this algebra is just a formal sum of the form. So we say sum over K from 0 to infinity and over all multi-indices, but with all the finite number of multi-indices. Okay, so let's call it multi-index. The multi-index will be denoted by I capital. So it should be less or equal to certain fixed number P. So it should look like H bar to the power K, A K, comma I of X. X are the local coordinates, and then we take y to the power I. So y, 1 through y to n are the local coordinates, which I already used, local coordinates on the fibers of the cotangent bundle, local coordinate functions on the fibers. And also y to the power I is just the product y1 to the power I1, yn to the power y2n, sorry, to the power I2n. Now, actually that's more or less what we need, save for one important technical thing. As you remember, I wanted to have the star product of two functions in the form of formal power series. So this formal power series means that I need to allow infinite sums, at least as far as h bar is concerned. I should allow infinite sums. And this is not hard to do, but in order to make this work, you need to introduce certain relations. So the easiest thing to do would be just to allow infinite sums over h bar. But that's not quite enough, unfortunately, again. Because in addition to allowing infinite sums over h bar, we also need, so to say, formal differential operators of arbitrary order. So I also need to allow arbitrarily long trains of formal variables y's, right? And this is a bit more tricky already, because when you take the product of two elements, then the number of these variables actually changes if you use the relation. fortunately enough, this relation involves h bar, and that's how philosophers managed to go through this difficulty. You remember that the relation is yi commutes with yj to h bar divided by square root of minus 1 pi ij. So pi ij is just a constant, or just an element in the functions. So these are just functions on the base. We don't care much about them. They commute with everything. They're just like scalar coefficients which appear in our Weyl algebras. So we should not pay too much attention to this, and also to square root of minus 1. But h bar is important because we want to allow infinite sums in h bar. So the idea is to transfer the infinite sums in y's to infinite sums in h bar somehow, because infinite sums over h bar are easily controllable. So what philosophy actually does, he says that let us introduce the grading. We put that the degree of variable y I is equal to 1, and the degree of variable h bar is equal to 2. And now this relation becomes homogeneous. And it means that however much we change the form of this expression, whatever we do with this, the total degree of this expression, if we take the sum of degrees of h times 2 and the sum of degrees of y, so actually it is 2k plus mod I, sorry. This degree will remain the same whatever you do. So after this observation, we just define W hat h bar of m is the completion of W h bar of m in respect to the grading. In other words, we allow infinite sums both here. Yeah, not here it used to be only up to degree n, but now we allow it to be infinite. And also we allow this to be arbitrary degree. The only condition is that the total degree of the terms which appear here should go to infinity. So as long as the total degree of these terms goes to infinity, this expression is valid. Of course, again, we can regard this as a section, as a space of sections of certain completed infinite dimensional now fiber bundle, we shall denote with W hat over it. But it is more interesting to look at this locally. So this is the definition of our algebra, now and for all. Before I proceed, I'll need to do few more, to describe a few more constructions which we shall need with this algebra. Okay, I'm going to erase this.
But
Yeah.
in the original definition of your elements, this number mod I was less or equal to what?
To p, to some p, actually. This should be not infinite, but also to some n. And this should also be only up to some p.
P doesn't depend on k?
Sorry?
P doesn't depend on k.
Well, actually, it should be double sum. Yeah, I mean, it should be just a finite sum. That's the only condition. It should be just
No
fine.
relation between p and k.
No relation in general. No relation. Yeah, but I just forgot to do one more thing. It is also convenient, although not necessary, to allow negative degrees of h bar. For many reasons, it's convenient for many reasons. So we shall allow k greater or equal to some minus p and then to infinity, and then the sum over I. Yeah, that's it. So we allow some negative degrees, but well, moderate negative degrees up to a certain, well, fixed number. We do not allow infinite sums in this direction, but starting with some negative degrees is always possible.
But wait, what is the definition? K is greater or equal to minus p or to
I mean, okay, I mean, if we allow these sums with negative degrees, so here, when I have this definition of Weyl algebra, I should allow negative degrees of h bar. That's all.
No, I mean, what's the definition of W hat then?
W hat is just the completion of, okay, so if we want to allow negative degrees of h bar, we have to start with this. And then we take completion over.
Yeah, I just ask what shall we assume about W hat? By definition, what is this? It is a completion of W with
Yeah.
with hat or with negative powers.
Well, I take W with negative powers, but without, yeah, but then complete it with respect to the grading. That's all. Yeah. So I just forgot to add this negative powers because it's actually not necessary for the construction. But for many technical reasons, it's just to, for instance, to keep certain relations in the classical form without h bar, unnecessary h bar.
But this makes this construction more difficult.
I don't see why.
Huh?
I don't see why.
Because of negative powers.
But we don't allow infinite negative powers, only finite.
You assume finite on the this definition, but when you complete.
But yeah, but I allow, no. Oh, I see what you mean. Yeah, sure, it can be. But I think when we complete, we should actually also limit the negative.
Then the definition is not correct.
Is it?
Because by your definition, the infinite negative powers are
Uh-huh.
permitted.
Right. If you just complete with respect, and we should allow infinite negative powers. Right. But okay, yeah, it's technical, but for a while. So in all expressions where we work, there will be no more than minus first power of h bar, and it appears only for the sake of nice.
Maybe
to keep
you should took the completion.
Yeah, and then
Positive powers, and then
yes, and that add negative. I just don't know. Yeah. Probably that's the right way to speak about this, because yeah, these two operations don't commute. Just yeah. Probably this is the best way to do. So you take the completion with all positive powers and then add negative powers, right?
Correct, please. This,
Okay. So this I erase this.
the right hand side.
I erase this and so this definition is correct.
Yeah, but your old definition was not correct.
This definition is correct.
No.
Well, before I start speaking about the negative degrees, this definition was correct.
No, I mean, now your definition is not correct because you corrected the definition of W.
Yeah, right.
Powers.
So, okay. So W without hat is all positive powers.
Rewrite this definition.
So W without hat was for all positive powers.
Repeat it on the
Okay,
because
you won.
not for me, for students
You think so?
online.
Okay, W without hat is just all positive powers. Of h bar. Then we complete it with respect to this grading. And then we add negative degrees. Finite negative degrees. I think it is done by multiplying the completion with tensor into with Laurent polynomials, right?
And then I have another question.
Okay.
By the definition, if in your own definition, if you have so if you just complete this all positive powers,
Yeah.
so there are no zero powers of H. Am I right to know?
Yeah. No, there is zero also. Non-negative. All non-negative.
No zero.
Yeah, all non-negative. Probably better to say non-negative.
This is important. But then still the completion is something very strange, because you allow infinite sums of y
Right.
to some power.
Yeah. But when you compute, when you change this power, h pops out and the degree is preserved. Pops up, so there is no problem with this now. Yeah, that's tricky, that's really important. Yeah, it's nice point. Then we add.
If you allow infinite powers of
Yeah.
y's, then why it's correctly defined?
Sorry?
Why it's correctly defined? I mean,
Well, here we have only finite non-negative powers. We begin with finite non-negative powers. Then we have grading, introduce grading. And this grading,
yes, I mean, what happens in your completion? I don't know.
it's a good question, I don't know, but I think this completion doesn't actually depend.
I mean, there is a problem with well-defined this algebra.
So, do you mean that this completion can fail?
Well, just apply the series 1 plus d plus d squared plus to infinity to the
Okay.
elements 1 plus x plus
Sorry.
squared. No,
Okay, 1 plus what?
plus x
Okay,
plus x squared
okay,
plus x cubed and so on.
right, okay.
Then by applying the first series to the second one, you will get an infinite sum of integers which will not converge. It's
So you take 1 over x, 1 x,
just powers of x, sum of powers of x,
okay,
and then apply this infinite series
of what?
1 plus d plus. So just try to commute them.
He probably means that subtraction yields the series with infinite negative degrees.
No, I'm not going to allow constructions with infinite negative degrees, definitely.
Not negative, just
No, that's not a problem with negativeness. I mean, you see, when you're not correct here, because when in our terms, when we commute a d and x, we get h bar. In this case, so you obtain an infinite sum of h of powers of h, and that actually corrects. That actually solves the problem. Of course, if it were not for h, your example would have been totally correct, but now h saves the yeah. Right.
So W hat contains negative degree sum
Yes.
by definition.
Yes, I mean, actually the construction goes like this. I first take finite powers, finite sums and finite powers of h bar and of y's. Then you introduce grading, and you complete it with respect to the grading, sticking to just positive powers. And then you add modestly negative powers of h bar by just tensoring what you already obtained with Laurent polynomials of h bar. And that's more or less it. If you just complete with when you allow negative powers of h bar, you can run into difficulty. because there will be infinite sums with negative powers.
But strictly speaking, you need to define what is a completion of algebra.
Yeah, sure.
It is,
Yeah, but
not,
yeah, it's not quite correct. But I think I've never seen in philosophers, probably in philosophers' books, he actually explained this in more detail. But in his papers where he introduces this, he definitely skips this. Yeah. Okay, so.
By the way,
Yeah.
we can also take negative degree, or
Of
degree is also always positive.
I mean, okay, the degree of h bar can be negative, but finite negative. So let me just write down the description of elements in local coordinates. So elements of this W hat, h bar of M, is now an element A, which is sum of, for k greater or equal to, well, equal to minus p to infinity, h bar to the power k. Yeah, probably also sum over mod I greater or equal to 0 of elements h bar to the power k, a k I of x, y to the power I, with the only condition, the sum 2p plus mod I goes to infinity in this sum. So there is only a finite number of elements in this sum with this gradient less than any given positive integer. Okay?
The degree of each term.
The degree of each term is just this. 2k, I forgot. 2k plus mod I.
Can it can take negative, or is it always
It can be negative because, for instance, if you take h minus first times certain function, just function on the manifold.
So in that case, the degree of this term is minus 2.
Yeah, minus 2, just minus 2. Yeah. Okay. So probably, I think that probably philosophers always just thought about elements of algebra in this way, in coordinate way. And that's why he actually doesn't.
This must be definition.
Um,
Because by saying that it's completion, it's not quite correct because it's not for non-commutative algebras. It's something.
Yeah, sure, but well, the theory. I think in gradient case, it doesn't actually matter if you have commutative algebra or non-commutative. In graded case, if you work with graded algebra, and we work with graded algebra here, definitely.
For commutative case, it's very low rating.
I mean, even if you work with graded algebra, you can actually work with commutative and non-commutative in the same way, when everything is graded, and that's just the purpose of having graded. When you speak about filtration, that can be quite different thing, but in case of grading, I think it's not a problem. Okay, we have this algebra. Nice. So one more thing before we proceed, just one more thing we need to do with this algebra. Actually, we have the following observation, which I already mentioned last time, but it is, I think, worth it. So consider a map from, so we fix again a point x0 in M, so we just consider the algebra W C h bar of R to n omega 0, that is to say, because all algebras of this sort are isomorphic to this one. So consider this algebra. And then we have a map from symmetric algebra of R to n with h bar, of course, and with complex coefficients. To this algebra W C h bar R to n omega 0. This map is given just by symmetrization. So if you have an element in symmetric algebra, it looks like a polynomial in variables y, y1 through y to n, with complex coefficients and with complex h bar linear coefficients. So with coefficients looking like polynomials in h bar, right? So that's more or less like this, yeah? So any element f in SC R to n is just a polynomial a0 of h bar plus a1 of h bar y some I, 1 I, and so on. So this is linear in y's, then there will be square, quadratic in y's, 2 ij h bar yj, and so on. Yeah, so it's just a polynomial in 2n variables with coefficients which look a little bit fancy, but that's not a problem. But the map from here to here just takes any monomial. So as far as the coefficients are concerned, they look pretty much the same, precisely the same on the left and on the right, the coefficients. Yeah? But the problem is that on the left, elements y1, y2, and y2n, so on, they commute with each other. And on the right, they do not commute. So what can we do with these elements? We just symmetrize them. So we take this monomial, yi1, yip, and send it to the sum over all permutations, sigma, in symmetric group of p elements, y sigma 1, sigma of I1, y sigma of probably, I sigma 1 is probably better, I sigma of 1, I sigma of p, right, and divide by p factorial.
This sum is infinite or finite?
Sorry?
I forgot what is SH.
It's just a permutation group. Oh, the left is just the space of this kind of polynomials.
Polynomial.
Yeah, just polynomials, just symmetric algebra. So we have the symmetrization map. This symmetrization map is linear isomorphism. As you can see easily from just the description of elements there, is linear isomorphism. Let's denote by sigma. So this is linear isomorphism. So it means that every element in W hat, so W without hat first, W h bar of M can be written as image of this map, right? Of sigma. So this gives us a way to write down elements in non-commutative algebra H bar as elements in commutative algebra. I mean, just linearly. This identification does not preserve the product, of course. But we can actually write down every element A in W h bar of M as the sum, now finite sum again, over k and I of the form h bar to the power k a k comma I of x. Now it depends on the point, of course, right? And then instead of writing y1 and so on, I just write it like this: y y, okay, mod I. Okay, this is a little bit, well, it's not correct to write it like this, but I mean that I look at this monomial that I have here. I look at the monomial which actually covers it from, I describe it as a combination of monomials in symmetric algebra. Every monomial on the right is a combination of monomial of symmetric algebra. So this is actually just a monomial in symmetric algebra. Okay? Or you can write it like sigma of y I1, y I mod y. Something like this, but I don't like sigma. Okay? Now this identification allows one to introduce the action, linear action, of the algebra, of symmetric algebra. Okay, let's put it like this. Maybe T star n on this Weil algebra. We just take any monomial, forget about the fact that it has sigma here, and multiply it by an element we want. Right? So every operation that we have on symmetric algebra is now transferred to some operation, linear operation. No more structure is preserved by this operation. But actually we have some well-defined operation on Weil algebra which comes from this linear identification. And that's all. For our purposes, we shall need the operation of multiplying by a certain element, certain coordinate function. So I circle will denote this multiplication here. And I also will consider the d over dy induced in this way. So I just take any element A in Weil algebra, replace all monomials by their images or pre-images in symmetric algebra, differentiate them over d over dy, and that's more or less it. And then send them back. This operation is by no means a differentiation in terms of Weil algebra product. It is just a linear map. Okay. Very nice. And of course, these operations and this identifications go in word-to-word manner from non-completed to completed Weil algebras. Okay, so this is now, the construction is now complete. And now I'm going to pass from this construction to the construction of the other important, the most important part of Fedosov's product is not this completion algebra and so on. This is of course more or less known and been known long before Fedosov. But what is most important in Fedosov's construction is the construction of abelian, or now they call it Fedosov connection. So what is the definition of connection? Let me recall you. Suppose you have a vector bundle. A vector bundle. Then you take, then connection on E is a map, linear operator from E to the tensor product of E with one forms, the bundle of one forms on M, which verifies the following condition. Nabla applied to F times S, and of course this nabla should be linear and everything over scalars, but the most important condition is that when you take the product of any element, any section, S is a section of E. If you take the product of this section by any function f on the base, then what you have is the combination of differential of f tensor S plus f times nabla S. I'll probably, to make this look better, I have to change the order in this tensor product. Of course, this doesn't matter in general, but to make it look correct, I think it's better to change the tensor product. Okay? So this is the definition of connection. In our case, we have a bundle of Weil algebras. Let me recall the notation. Either completed or non-completed, doesn't matter. I have this bundle, right? And we want to introduce a connection on this bundle. So this means that we need to introduce a map from sections of this bundle, which are denoted by this symbol, to the tensor product omega 1 tensor with the same space. So this tensor product is actually can be regarded as a space of differential one forms on the base with coefficients in Weil algebra, and elements of this tensor product, or more generally of this tensor product for arbitrary I don't know, Q, look like, well, alpha is equal to the sum of the form A k I j h bar to the power k. Now take y to the power I and dx to the power j. So I and j are multi-indices, and the sum over k and I can be infinite, just as we described it before, and the sum over j is always finite. Doesn't matter, whatever we do, right? So any element here is of this form, and we regard connection as a map from a space of sections of the algebra. So from this space, from the space of x sections of this algebra bundle, to the space of differential one forms. The problem is that we want this map to somehow preserve the product. Well, as any differentiation, it can only mean that this map, as explained, connection is a differentiation in some sense, right? I've just erased the Leibniz rule for this connection with respect to the multiplication by functions. So connection is a covariant derivative. It is actually it verifies Leibniz rule. So we wanted to verify Leibniz rule with respect to the product of the elements of the Weil algebra section, or Weil algebra bundle. So we want it to verify the following identity. For any two sections, alpha and beta, when you take the derivative with respect to nabla, you obtain the product nabla of delta, or nabla of alpha times beta plus alpha times nabla of beta. Now, Of course, when you have tangent bundle, say, or cotangent bundle of a manifold M, and you take a tensor product, tensor power, then the usual connection, actually any connection on tangent or cotangent bundle extends to this sort of map, as you probably know, because it is one of the standard conditions imposed on connections, that it verifies Leibniz rule with respect to the tensor product of tensors. It's the way the connection is extended from tangent bundle or cotangent bundle to the tensor bundle. Now, while algebra bundle differs from this kind of bundle only by the fact that we introduce certain relations. The relations look like the commutator of yi and yj is equal up to a certain coefficient, which is totally fine because this coefficient is just a scalar number, times pi ij, and this here coefficient unfortunately is not constant. It is an element, it is a coefficient of the symplectic form, or actually of the inverse of the symplectic form. So what we need now to preserve this Leibniz rule, when we pass to the quotient of the tensor bundle by this relation, we need to make sure that this relation is killed by our connection. So when we apply nabla to the left-hand side, what you obtain is it is just nabla I. So in tensor algebra we have this. Right. So and then when you subtract it, it should be equal to 0. And then subtract it, and you obtain h bar divided by square root of -1 nabla of pi ij, right? So you want it to go to 0. You want this to hold. You want this to be just the how do you call this? You want this to be let me see. So, well, what you really want, you want this nabla of yi times yj should be equal to nabla I yj plus yi nabla yj. So it means that only this should survive our relation, right? Only this should survive. And this should go to 0. That's what we want, right? And this brings us to the following definition and the following theorem, which is, of course, classically known and was known before Fedosov, but which now is, I think it brings, it gets some new light from the role it plays in Fedosov's construction. Definition theorem. Let, again, M omega be a symplectic manifold. Then there exists connections, well, probably exist connections because it's plural. Nabla on T of M on tangent bundle, and hence on cotangent bundle as well, as you know, such that, well, first of all, they're symmetric, that is torsion-free. And second, nabla of omega is equal to 0. These connections are called symplectic. Before I prove this theorem, I just want you to take a look at this. If you change symplectic form in this relation by Romanian metric, then you probably have heard that such connection exists and is unique. This is the Levi-Civita connection, or symmetric Romanian connection, which is unique on any Romanian manifold. Unlike Romanian case, in symplectic case, the existence of connections does not mean that they are unique. Does not imply uniqueness of these connections. So I'm going to prove the existence, and yeah, and then it will be probably a good exercise for you to see where I actually lack the uniqueness, what place of my reasoning is where I can change to make it work, to introduce non-unique connections. Okay, proof. Well, I'm not sure that I remember this by heart, so I'll probably take a look at my notes for a while, once in a while, but okay. So I begin with the following observation. Take any symmetric, distortion-free connection. Even Levi-Civita connection for arbitrary Romanian structure will do. Nabla 0. And apply it to omega. Nabla 0 of omega needs not be 0, so for any two vector fields, x, y, and z, we have the following identity. So we take, not identity, we can consider the following tensor. We take nabla 0 sub x and apply it to omega, and then compute it at y and z. So this is just nabla 0 of x applied to omega yz, which is just the x of omega yz, minus omega nabla 0 of x, so sub x of y, z minus omega y nabla 0 sub x, z. So what you have on the right is actually an expression dependent on three vector fields. That's denoted by, I don't know, f of x, y, z. It is easy to see that if you change the vector field x by f times x, then f will come out of f. You have this. So this is linear over functions with respect to the first argument. And then you can take the second argument, for instance, and take y. And then you use Leibniz rule to see, and you see that the difference between the f linear part and non-f linear part will cancel out, because it will come from this place and also from this place. So what you see is that actually f of x times f times y z is again equal to f x y z. right? So it is linear over functions with respect to the second argument, and then the same is true for the third argument as well. So what we have, we conclude that F is actually a three-linear map, and it's such in this way, in this sense, it is a tensor. I think it is 0,3 tensor over on our manifold. It's a tensor field. Tensor field. Then we go on, and we observe that any tensor field on symplectic manifold, since symplectic form is non-degenerate, any tensor field of this form can be written in the form of the following combination. Is equal to omega of certain two tensor field x, y, and z. And this is just because the symplectic form is non-degenerate, right? Now, of course, n is symplectic form. Sorry, n is tensor form of is not 0,3, but 1, 2 tensor, right? It is 1, 2 tensor. Nice. What else we can see? We see that since omega of yz is equal to minus omega of zy, we can change the order of y and z here, and this will give us the sign, right? And also here, oh, sorry, we can change the order here, and here, and here. And this will give us the sign on one hand. On the other hand, we shall have f x zy, which is equal to omega n x z comma y, right? So we have this formula again. Okay? And it's just the, well, in terms of coordinates, it's just the region of the indices with the help of omega. But in invariant terms, it's just the 1, 2 tensor, such that f is equal to this combination of tensors.
I mean, you could write down the label for students.
Oh, I said it. I mean, I think if you are familiar with linear algebra, you see that if you have a scalar valued tensor f x y z such that it is just some real number, a complex number, doesn't matter.
It's okay. I mean, just to fix a notation.
Well, I think I said it, but what do you mean? What's the problem? You mean I need to write it down in coordinates with indices?
Just fix notation.
So yeah, okay. I said that there exists a unique 1, 2 tensor such that f is equal to this expression.
I mean, you can just
Okay, n is the unique 1, 2 tensor such that one fixed equation star holds. Okay. And then we have this identity as well. So minus n omega n xy comma z is equal to minus omega n xz comma y. Or in other terms, omega n x y comma z plus omega n x z comma y is equal to 0. Right? So we have this identity. Also, since nabla, since the symmetrization, skew symmetrization of the covariant derivative of any differential form is equal to the differential of differential form, right? You see, if you have a covariant derivative with respect to any symmetric connection, then symmetrization of this covariant derivative is equal to the differential of the differential form. Is this known? Okay, in code, this is an exercise. In indices, it means if you take nabla I omega j k and you take skew symmetrization, it is equal to d omega I j k. And since omega is closed, it is equal to 0. In invariant terms, it means that symmetrization of f symmetrized, skew symmetrization is equal to 0. But what does it mean to have skew symmetrization of f? We have f, x, y, and z. And this expression is skew symmetrical already in two terms, in this and this direction, right? So its skew symmetrization actually amounts to taking cyclic permutations of these three arguments and taking their sum divided by 3. So it means that 1/3 of this plus this plus this is equal to 0. Well, 1/3 is not necessary actually. 1/3 is just to restore the coefficients, right? But still it is worth it. And if you restore this n symbol, it means that omega n x y z plus omega n y z x plus omega n z x y is equal to 0. So we have these two relations, number 1 and number 2. And now here's the trick. So if you have a connection and if you add to this connection a tensor, a 1-2 tensor, then you again get a connection. So what I'm going to do, I am going to add tensor n to the connection, symmetric connection nabla. The only problem is that I want to make it symmetric. So I symmetrize my tensor. So up to the coefficient which I will try to restore. I put nabla of x applied to y to be equal to nabla 0 sub x applied to y plus, well, 1/2, I'm not sure about this, but let it put it 1/2 first, of n xy plus n yx. And then claim nabla is symplectic connection. Well, as it is of course symmetric, so the only thing we need to check it is that nabla of omega is equal to 0. So I just wonder if I need to check it right now. I want to need it to leave it exercise as an exercise. Okay? I just don't know whether I should leave it as an exercise or prove it. I can do either. Yeah. Just to make sure. Okay. Sorry, it's not 1/2, it's 1/3. Yeah. It's important to keep the coefficient correct. Oh, anyway, so if you want, I can check it for you. So this is symmetric connection, and we only need to check that the symplectic form is killed by this connection. So what we do is this. You take nabla omega and compute it at vector fields x, y, and z, as we did before, right? So I skip lots of computations and just write it down. So the first term will look like nabla 0 x of omega of y and z. That's precisely what I had before, right? It's omega of n x, y, z, right? But when we have, yeah, and also, yeah, just so I leave it as an exercise for you to check that the sign is correct. So it's just minus 1/3 of omega n x, y, z plus omega of n y x z plus omega of y n x z, and finally plus omega of y and zx. So the second and the third and the fourth term appeared from the fact that when we write down this expression, we shall apply nabla to the first element first, and then to the second element inside omega. So that's why these two terms appear. Right? Okay. Now, if you now write this down as a 3 times 1/3, few things will cancel out, and we shall eventually get this expression. It is equal to 2/3 omega n xy comma z minus 1/3 of omega n yxz plus omega y comma n xz, and finally omega y and zx. And in the very end, we shall see that this expression actually can be written down as a combination of two sums. First sum is 1/3 omega n x, y, z plus cyclic permutations. So it is equal to 0 by the equation 2. And then we shall have 1/3 omega n x y z plus omega n x z y. And that cancels out by the equation 1. So it's also cancelled out due to this symmetricity. Yeah. Yeah, but still, please check that there is a freedom of choosing this correction term. So as you see, my symplectic connection appeared as a correction of the original symmetric connection by a certain correction term. And please check that there is a freedom choosing these correction terms. Okay, I think that I'm running out of time rapidly. How much time do I still have? Oh. Yeah, maybe less. It's definitely, I'm definitely going to continue next time. Yeah, it's minus 5 minutes. I remember I once was in Poland at a seminar, and they said that, how much time do I still have? The professor asked. And they say, minus 5 minutes. Somebody tried to joke, and they said, tyle mnie wystarczy. It will be enough for me. Okay, I'm not that self-assured. I'm not sure that minus 5 minutes will be enough for me. But I try to at least explain what we're going to do next. So that's just the beginning of the long story. I'm sorry for this. It took me much longer than I expected because we had to speak very carefully about the Weyl algebra and its completion. Yeah, it is important, but actually, philosophy himself skips this, just writes that we completed and that's all.
Well,
Right,
exactly,
right.
because the completion, notion of completion itself is very complicated.
Yeah, I see.
Simple objects like commutative ring.
Sure. Yeah, I understand this. I totally agree with you. I totally agree.
When you skip, what do you mean by this?
You should be careful when you talk about this. So for philosophy, it was enough to have explicit formulas. So he just spoke in terms of explicit formulas.
That is the point.
Yeah. But yeah, I think it should. Yeah. By the way, another exercise, as we speaking about explicit formulas, another exercise would be to find the explicit formula for the correction term, which I just wrote here, in coordinates, that is to say, with indices. It turns out that the correction term, so any connection, as you know, can be written down as the combination of the usual de Rham differential plus gamma ijk, right? Gamma ijk are the Christoffel symbols. So it turns out that, and what we have just done, we have started with some Christoffel symbols and then added some correction term, which philosophy denotes by delta ijk to it. And one can actually write down the expression for this correction term in terms of the symplectic form itself. I think it's a good exercise for you to find this expression. Okay, so next step, just what are we going to do next? That means next time. So now we have a vector bundle omega, so W hat, and we consider its sections, W hat sub HM. And we want to construct a connection. So we begin with symplectic connection, and symplectic connection gives you a map from this bundle to its extension by differential forms, and I'll note this extension by just adding 1 here. right? Then, of course, you can repeat this procedure just using the same Leibniz rule. If you have a tensor product of a differential form alpha and a section S, and you use Leibniz rule and obtain differential like this. Right? So this extends any connection you have to a series of operators. So here you have differential two forms with coefficients in connection, in Weyl algebra and so on. If you have ever seen, well, if you have ever worked with homological algebra, you can probably guess what I want to do next. I want to consider this sequence of operators as a chain or cochain complex. The main problem is that this is not a cochain complex unless the connection is flat. What is flat connection? It is a connection such that its square is equal to zero operator. Of course, not every manifold allows flat connections. To have a flat connection, one has to be a very special manifold. So in general, we only have a non-flat connection, and in this case, you have a very nice formula, actually. Nabla square applied to any section A here will be equal to the commutator of the differential form omega of y with A. So omega of y is an element in differential two forms with coefficients in Weyl algebras. So omega of y lies here. And it can be written very explicitly in terms of the curvature, usual curvature of the symplectic connection we have. Namely, what can we do? As you know, curvature of any connection is a differential two form with coefficients in endomorphisms of the tangent bundle. So in our case, we have differential form omega of the form locally, in local coordinates, locally, of the form omega ij times dxp dxq. So probably you should also write pq here. So omega ij, so if you forget about this, you just get a matrix valued function. So you have a differential two form with coefficients in matrix valued functions, with coefficients there. Then you can use symplectic form omega to lower this index. So what we get, we lower this index and we denote omega ij comma pq to be equal to the lowering I k omega kj comma pq dxp dxq. So now what we have on the left is just a differential two form, locally defined, of course, because when we change coordinates, these two indices behave not in an appropriate way. They behave a little bit, well, awkwardly. They're not just what we need. Now this can be cured. We just take omega y to be the sum omega I j y I y j d, well, of course, pq is also here somewhere, dxp dxq. That's precisely the element in differential in this space. This differential 2 form with coefficients in the Weyl algebra. And then one can easily check this relation up to the coefficient which I need to restore. The coefficient should be, just a moment, the coefficient is necessary because there is this coefficient h bar divided by square root of -1 in the commutation relation. So this coefficient here, it looks like, let me see.
You promised to neglect such a coefficient.
Oh yeah, you're right, but still, this coefficient is square root of -1 divided by twice h bar. So we shall, if we neglect it, then there is no problem at all. But if you want to make everything, well, up to the point, then you need this coefficient. So check this formula. So this formula is very promising because there is one thing which philosophers observed in this case. In this case, there is one thing which actually saves the whole day. Namely, this commutator can vanish even if the first term is not 0. This commutator vanishes identically for all A if the first term is in the center of the Weyl algebra. And the center of the Weyl algebra is spanned just by differential 2 forms on M with coefficients in h bar. So now the question is, if we are able to change my connection nabla somehow by adding some correction terms so that the resulting connection will have curvature belonging to the center of the Weyl algebra. Philosophers called such connections abelian connections. Nowadays they're called philosophers' connections. And the next thing I am going to prove, and this will probably be next time, that such connections exist, and there are much more than just one of them. I'll probably prove the existence theorem, but I'll just sketch the proof of the classification theorem, because this classification is actually quite a long story. I just want to skip the details. But the idea is very simple. The idea is very simple from the very beginning. We want to add correction terms to omega, sorry, to nabla. We consider nabla plus correction term. And then we find correction term. We solve the equation, which will provide us with the central curvature. And that's what I'm going to do next time.
And is it possible to give some explicit example?
Explicit example.
For example, very simple manifold, and write down such a pillar connection for them.
It's a good exercise to be sure. The problem is that local. So if this manifold is non-trivial, then just writing down explicit formulas for the symplectic form is non-trivial. So actually you can find the first few terms in this connection. There is a procedure, the procedure which I'm going to talk about next time. It will give you some automatical way to find the first few terms in this in this correction term. However, the whole series can be, well, I don't think it is possible to, in any non-trivial case, to find all terms in some closed form, some closed way. First few terms is doable, definitely. Yeah, but in general case, it's always the thing here. The famous Kontsevich universal formula, it's also quite remarkable in the fact that it gives you some very explicit way to write down coefficients of the deformation series. It looks, these terms look like for differential operators with certain coefficients. But when you try to find out what are those coefficients, it turns out that those coefficients are some integrals of very complex form. They are, so just to compute the third one, the third coefficient, I think it was a big achievement in the beginning of the 2000s when the first coefficient was finally computed completely. Okay, so next time I'll go on from this place. I'll start from this place and just, I think it's a good exercise to check this formula. It's a good exercise for you to check this formula. I'm not going to make this exercise, but making it is a good is good for you if you want to understand this story completely. Okay, now that's all I wanted to say. Shall we stop here? Are there any questions or comments? Yeah.
The claim is that there exists such
Yeah.
omega.
Yeah.
That
there exist such correction terms. One can change my connection by adding some correction term, just what I did before, but this time I'll have to involve the Weil algebra structure. So I'll change my connection by adding some correction term so that the resulting curvature, resulting term here, will be in the center. Mm-hmm. And moreover, there will be many such different connections. That will be, that's what I'm going to talk about. But that's just the beginning, because then I'll have to prove that with this connection, the space of flat sections will be isomorphic, linearly isomorphic to the space of functions, and that's also it also will take some work. And then
many reasonably different corrections. I mean, you could always add some d something and
actually, as far as this correction term is concerned, it is easy to guess what it should look like, because I told you that we want to make our connection a differentiation in Weil algebra. But if you have heard about Weil algebra, you probably have heard that Weil algebra does not have any derivations except for what they call inner derivations. And inner derivations are just commutators with elements of the Weil algebra itself. So we can only add commutators with elements of the Weil algebra. And it turns out that we can add these correction terms, add these commutators in such a way that the result will be central. And which is worse, I think I can unveil this mystery right now, which is worse, we can make it in as many different ways, as many different closed forms there are on the manifold. Substantially different closed forms. Closed two forms, sorry. In other words, we can obtain any set, any series of classes in degree 2 de Rham cohomology of our manifold as the curvature. And the theorem will be that there are as many different Fedosov connections and hence as many different Fedosov quantizations, as many different series of degree 2 classes in the RAM form, in the RAM cohomology there are. So everything is classified by degree 2 de Rham cohomology. Just it. So that's what I'm going to talk about next time, and that will be probably the last time I speak. So if anybody wants to make a talk, please let me know. You can talk, for instance, in my opinion, the closest thing to what I have been talking about and what you can discuss here about what you can make a presentation is the way this construction works in complex case. In complex case, it turns out one can make few important corrections, few important changes in this construction so that the classification theorem will be different. You can actually what you will get will not be spanned by the whole degree 2 de Rham cohomology, but only by some part of the Rham cohomology. And that's quite interesting thing. Just to reduce the number of different quantizations if you want to preserve holomorphicity of your functions. That's an interesting thing. Okay. If there are no questions, then I just stop this, stop my conference. Thank you for attending it, and goodbye. Слушайте, я думал, что я быстрее пойду. Что-то я совсем...
Ты еще на следующий раз расскажешь.
Получается так, да.
Ну, на самом деле, это ничего удивительного, потому что конструкция становится все сложнее. Как-то странно было бы быстрее объяснил то, что...
Ну, да, это верно. Это верно. На самом деле, философская конструкция очень богатая. Она там может быть... Во-первых, из-за того, что она геометрична, она дает выход на очень много разных вещей. Она в некотором смысле даже более геометрична, чем концевическая. Концевическая она такая, может быть, сделана геометричной, но все равно она очень быстро уходит в какую-то абстрактную такую алгебру. Очень абстрактную, такую теорию категорий, там все, в общем-то. С ней сложно.
Ее Концевич уводит.
Ну, непонятно, потому что там, может, природа такая у нее. Она может дело в том, что Концевич дает универсальную формулу. Концевич дает универсальную формулу. Философ дает формулу только для симметрического модела. И поэтому философ не такая универсальная, но чем-то проще, при этом она задевает и геометрию. Концевич, она там геометрию выйти, сильно работать. Интересно.
Ну, вот интересно, такая ситуация. Если у меня многообразие не симметрическое, а функциональное, если я функция факторизую функцию, оно наслоится наслоением.
Понимаю, да.
А вот
у
меня получится куча синтетических листов, листов. И вот между этими листами, они с точки зрения алгебры, они не сильно отличаются. Ну, вот эти сферы на высоте. Вот мы радиус 2, у другой радиус 5. Грубо говоря, никакой разницы. Ну и, наверное, вот эти конструкции тоже
Я согласен между этими всеми конструкциями и даже между